Ciba-Geigy is color. Ciba-Geigy is pharmaceuticals. Ciba-Geigy is plastics and additives. Ciba-Geigy is agricultural products and many different specialty chemicals. And most of all, Ciba-Geigy is people. Thousands of people and thousands of products, all dedicated to making life better and healthier. The Science Screen Report is proudly presented by Ciba-Geigy. The Science Screen Report, bringing you each month the latest discoveries, developments, and applications of science, engineering, and medicine, made to solve the problems of modern life. How did the continents come to have their present shapes? And the moon acquire its empty seas and great craters? Scientists now know the Earth and Moon are over 4 billion years old, but their knowledge of the events and processes which formed them and which continue to reshape the Earth is still very incomplete. One reason is that almost all the Earth's ancient rocks and formations have been altered by extensive volcanic activity, erosion, sedimentation, and other geological processes. The remaining ancient records have been largely inaccessible. Two major research projects now in progress are making these geologic records more accessible. Because almost all of the rocks brought back from the moon by the Apollo astronauts are more than 3 billion years old, they can be studied to give clues about the Earth's origin as well as the moon's. At the same time, the Glomar Challenger drill ship, sponsored by the National Science Foundation, is sampling selected deep-sea sites around the Earth. This issue of the Science Screen Report details how, through both projects, scientists and engineers are seeking a new understanding of the events and forces that formed and continue to shape the Earth. The data returned by the remarkable Apollo moon flights, as well as unmanned space probes, enable scientists to infer much about the formation of both the Earth and Moon. Analysis of the moon rocks has shown that the moon's chemical makeup is distinctly different from the Earth's, the Sun's, meteorites, and probably other planets. Compared with Earth, for example, the moon rocks are richer in calcium and aluminum, poorer in sodium and water. The new data suggest the moon, Earth, and other planets each formed independently, starting as bodies a few kilometers across and growing by accretion, which is the accumulation of objects drawn together by gravitational attraction. These objects range from dust particles to asteroids. About 4.5 billion years ago, the moon, Earth, and other planets had reached their present dimensions. During the latter stages of this accretion process, collisions may have generated so much heat that the entire outer shells of the moon and Earth were seething global oceans of molten silicate materials. As the bombardment slowed, the liquid shell of the moon began to cool, solidifying over a period of millions of years. Crystals rich in calcium and aluminum formed, rose to the surface, and produced a mush which solidify to become the light-colored material we call the lunar highlands. During the same period, dense crystals rich in magnesium and iron formed and sank, making a distinct dense layer. There was now a lunar crust, a product of millions of years of crystallization. 100 to 300 million years later, radioactive heating probably became extensive enough to melt materials in the shell just beneath the crust. The melting produced pockets of lava, giving rise to volcanic eruptions 4.4 to 4.3 billion years ago. At the same time, globules of molten material rich in metallic iron may have accumulated and settled down into the center to form a core. If 2 to 3% of the original moon consisted of metallic iron, the core may have a radius 1/5 that of the whole moon. Such a differentiated moon with a crust, a mantle, and a core resembles the three-part structure of the Earth. It now seems likely each of the inner planets has some type of differentiated structure. A molten iron-rich core, like the Earth's core, could function like a huge dynamo producing a magnetic field. This may account for the magnetism in many lunar rocks brought back by Apollo. Even 500 million years after the crust was formed, colossal objects were still impacting the moon. The final ones blasted out its great circular basins like the Mare Imbrium. By this time, about 3.9 billion years ago, the crust of the moon had probably cooled to a solid. By contrast, the interior began to warm up from natural radioactivity. 300 kilometers down, a zone melted, producing liquid silicate material pockets. The molten silicates were forced to the surface through crust fractures, or by making new passages through the crust. Successive volcanic flows filled in the great basins blasted out by the meteoroid impacts and became the lunar seas. After 1.5 billion years, major volcanic activity on the moon seemed to end. Except for occasional volcanic activity from the lunar interior, rare meteoroid impacts like the one which made crater Copernicus, and small moonquakes, the geology of the moon has not changed for 3 billion years. The differences in global activity on the moon and Earth can be summarized on a graph. It seems clear the moon had a violent, dynamic early history, but that major geological activity came to an end 3 billion years ago. It is likely that the Earth had a similar early history, but unlike the moon, its geological activity has continued. About 500 million years ago, hard-shelled animals appeared whose fossils can be found in rock formations. About 250 million years ago, the process called continental drift began, a process now being studied via the drill ship Glomar Challenger. This is the Glomar Challenger, a very special ship that's helping reveal the Earth's history. Since 1968, its drilling and sampling at selected sites around the globe has provided a new understanding of the structures of the oceans and continents. Its first leg was to study the mid-Atlantic ridge. Magnetometer readings showed bands of rock of alternating polarity, north-south, south-north, north-south, and so on, extending outward from the ridge. These alternations may reflect the alternations that are thought to have occurred in the Earth's geomagnetic field when the north geomagnetic pole changed to the south geomagnetic pole and then reversed to the north again over millions of years. As new lava emerged from the ridge and cooled, it was magnetized according to the direction of the field at that time. The Glomar Challenger found further confirmation of this sea floor spreading. Taking cores on both sides of the ridge, the drill ship scientists analyzed the fossil record of sea life in the cores and found that the older strips were further from the ridge on both sides, evidence that the continents are being driven apart at the rate of several centimeters a year. Further legs led to more discoveries. In the Pacific Ocean, a major part of the seafloor had moved from the equator to near the Aleutian Islands, 4,000 kilometers in 125 million years. 5 million years ago, the Mediterranean was blocked off from the Atlantic by a movement of the Atlantic plate. The Indian Ocean included a vast volcanic chain of islands and coal swamps some 65 million years ago. The Indian subcontinent broke away from a huge supercontinent, moved north, collided with the continent of Asia, and created the Himalayan mountains. Similar dramatic finds were made in other regions. New findings pour in with each new drilling. All these discoveries support the theory of continental drift, that the present continents split off from one or two ancient supercontinents and are still slowly shifting about the globe. But what determines their movements? A theory called plate tectonics states that there are a dozen or so giant plates forming the Earth's outer shell. The continent and ocean floors are carried on the plates, which float on dense plastic rock below. Plate interactions take various forms. When plates come together, one may slide under another, forming ocean trenches or starting volcanic activity. Or they may drive against each other, forming mountains. Plates may slip against each other, causing cataclysmic activity, huge faults, and earthquakes. And when plates move apart, subcrustal matter boils up to the surface to fill the gap. This seems to be happening in the mid-Atlantic ridge. Geophysicists are not sure what drives the plates. One theory states they are set in motion by massive heat currents in the hot plastic material below. Another states that local hot spots or heat plumes move the plates. The work of the scientists aboard the Glomar Challenger has provided additional interesting data about plate movements. In the Pacific, the major plate is moving away from a spread in mid-ocean, so the ocean floor is creeping under the Asian continent at a rate of 10 centimeters a year. Also in the Pacific, evidence was found for plate movements in the form of sea mountains, some thrusting out of the water like Hawaii. More data is needed to determine if such mountains were made by a plate moving across heat plumes. And along the eastern Pacific Rim, another Pacific plate is also moving away from mid-ocean, under-thrusting the American plate at the rate of 5 centimeters a year. These and other findings have given us a picture of massive plate movements and their consequences. The major plates are now clearly defined and drawn on a map of the Earth. Their boundaries delineate belts of volcanoes and earthquakes, dramatic testimony to the great forces at work, forces we are just beginning to understand. Though the Apollo program is over, the 1,700 kilograms of lunar rock samples, thousands of photographs, and kilometers of magnetic tape data have only begun to be analyzed. While the Glomar Challenger continues to probe the Earth's prehistory, inferring from the ancient rocks and sediments the autobiography of our own world. From all this research may come a better understanding of the birth and evolution of our planet and the biographies of the other planets and the solar system. In fact, cooperation among the various branches of science and engineering are leading to whole new interdisciplinary studies such as planetology. Through learning what came before, scientists are better understanding what is happening now and what may happen in the future, both for its own sake and as keys and guidelines to earthquake prediction, new resources, and other potentialities of Spaceship Earth. Science Screen Report has been presented by Ciba Geigy Corporation, with headquarters in Ardsley, New York, as part of its continuing program in support of science education.